Hello everyone. Today we're going to talk about the Shoelace theorem, which in my opinion is a must-know theorem for the AMC and the AIME. It just helps so much when you're trying to find the area of some sort of polygon. So, the Shoelace theorem gives you the area of a polygon given the coordinates of the polygon. So, let's say the coordinates of the polygon are x1, y1, x2, y2, all the way to xn, yn. The area of those points, the area within those points is this: 1/2 times the absolute value of, in parentheses, x1, y2 plus x2, y3 plus x3, y4 all the way to xn times y1. And then close the parentheses and then subtract, in parentheses again, y1, x2 plus y2, x3 plus y3, x4 all the way to yn, x1. Now you might be thinking why it's even called the Shoelace theorem. That's a pretty weird name for it, but actually it's because when you're multiplying stuff like this, then it kind of looks like a shoelace pattern, because keep in mind, x1, y2 plus x2, y3 plus yada 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 x1, xn, y1. As you can see here, down to the right, x1, y2 plus x2, y3 plus x3, y4 all the way down to xn, y1. And then you subtract. Now you go down and to the left, y1, x2 plus y2, x3 plus yada 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 yn, x1. yn, x2 plus y2, x3 plus yada 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 yn times x1. So, you know how a shoe has like laces and the laces kind of look like crossed? So yeah, that's why it's called the Shoelace theorem. So let's just do a quick example. If 0, 5, 1, 3, 3, 2, 1, negative 2, and negative 2, 2 are vertices of a polygon X, what is that polygon's area? So if you try to do this in the quote-unquote normal way, it's going to be very difficult. You're going to have a really weird polygon, and you're going to have to add areas, subtract areas. It just won't be very quick. But with the Shoelace theorem, it will be very quick. So the first thing, and I forgot to say this, I'm sorry, is that we have to write our points up, down in a clockwise fashion. So luckily for us, the points here were written in the clockwise manner. So we just have to write 0, 5, then 1, 3, then 3, 2, then 1, negative 2, then negative 2, negative 2. And, sorry, another thing I didn't say is that you have to write the first point again at the end. 0, 5. So we have this. Now we just plug our points into the formula. So let's do that. So it's 1/2 times the absolute value. Remember, we have the absolute value because area cannot be negative. It has to be positive. So first one, remember, down to the right. 0 times 5. That's 0. Plus 1 times 2. That's 2. Plus 3 times negative 2, that's negative 6. Plus 1 times 2, that's a 2. Plus negative 2 times 5, that's minus 10. And let's put that all in parentheses. And now we subtract. And we do the same thing, but down and to the left. So minus 5 times 1, that's 5. Then plus 3 times 3. So that's plus 9. Then 2 times 1, so that's plus 2. Then negative 2 times negative 2, that's 4. And then 2 times 0, well, that's just 0. And now, just basic arithmetic. 1/2 times, let's see, 0 plus 2 minus 6 is negative 4, plus 2 is negative 2, minus 10, negative 12. So times the absolute value of negative 12 minus 5 plus 9, 14, plus 2, 16, plus 4, 20 is 20. Now we just subtract. So we get minus 12 minus 20, so that's minus 32. So that's 1/2 times the absolute value of minus 32. Take the absolute value of minus 32, you get 32. And then divided by 2, you get 16. And that is the area under the vertices of these points. Now, in the next video, I will prove this formula, which can be a little difficult, but I promise as long as you look at it and you think about it, it's pretty easy to prove. And just one more thing, notice that in the Shoelace theorem, as you can see over here, if you know anything about matrices, this kind of looks a little bit like, if you know anything about matrices and vectors, this formula kind of looks like the cross product. I'll let you think about that by yourself, but keep in mind, in order to prove this, we actually have to look at vectors. And then we notice that if we manipulate vectors, we get this formula. So, that's some food for thought for all of you matrices and vectors fans. But anyway, if you have any questions, please let me know. I'll probably do another example in which it's a much more difficult question and we still use the Shoelace theorem to skip a lot of steps. But that'll be in the future, and I will prove it in the future once again. So yeah, have a nice day.